Alright guys, for this problem, we had problem 41 on page 236 of the textbook. You have a softball player swings a bat, accelerating it from rest to 3.0 revolutions per second in a time of 0.2 seconds. It's called approximating, wrong there. Approximating the bat as a thin rod of length 0.95 meters and mass 2.2 kilograms. Calculate the torque applied to one end of it. Okay, so I'm recognizing by reading this problem that this is a Newton's second law for rotation problem. And the reason I know that is because the information I'm given in this problem indicates how the bat changes its rotational motion. And it also indicates some properties of the bat that would help me to find its moment of inertia. It's a thin rod, we're given its length and its mass. Okay, so ultimately what I'm going to do here is I'm going to use Newton's second law for rotation. So we're going to do alpha equals net torque divided by I, which we'll rearrange and write as net torque equals I times alpha. Okay, so we need to find the moment of inertia I, and we also need to find the angular acceleration alpha, and then we can multiply those together to get our answer. So they tell us to approximate the bat as a thin rod of length 0.95 meters, mass 2.2 kilograms. If you think about how a baseball bat is swung, it's swung from the end, not from the center. So we could look up in the table what the equation is for the moment of inertia of a rod about its end, and we would find that it's 1/3 ml squared. So we can use that here. We can do 1/3 times the mass, which is 2.2 kilograms. Whoops, 2.2 kilograms times the length, which is 0.95 meters. And we're going to square that. And that's going to give us our moment of inertia. So let's try that. So 0.33 times 2.2 times 0.95 squared. I'm getting 0.655. So let's put that in 0.655 kilogram meters squared. Okay. Now, to find the angular acceleration, it's not given. It says it starts from rest and it gets up to 3 revolutions per second, but I don't like working with revolutions per second. I want to get that in radians per second. It's already seconds, but we have revolutions, not radians. So we need to multiply this by 2 pi to get it in radians. 3 times 2 pi would be 6 pi, which is about 18.84 radians per second. Okay, so now we can find alpha. So let's work that out over here. I'm going to change colors. So alpha, is going to be the change in angular velocity over the time. So we're going to get 18.84 radians per second minus 0 divided by the time of 0.2 seconds. Okay, so if I do 18.84 divided by 0.2, I'm getting 94.2 radians per second squared. So that's my angular acceleration. I have alpha. I can multiply those two together to get the net torque. So the net torque is going to be I times alpha. So 94.2 times 0.655, and I'm getting 61.7 units are going to be Newton meters. And we're given two sig figs here, so we'll say 62. So notice that I used this Newton's second law for rotation to solve this problem and not torque equals F times distance times sine of angle. The reason for that is context. What we're told here is information about the rotational motion change and also about some properties of the object so that we can find its moment of inertia. So that clues me in to using this version instead of distance times force times sine of angle. So hopefully that made sense. Let me know in the comments if it didn't or if you have more questions and we can go from there.